Welcome to The Explainer. Today, we're zeroing in on a pretty massive shift happening in modern data architecture. We are going to explore exactly how distributed systems are evolving, moving away from those fragile, synchronous web services we're all used to, and towards incredibly robust, scalable architectures powered by event streams. So, if you've ever wondered how the back ends of the world's absolutely largest platforms actually hold it together when traffic suddenly spikes, you are in the exact right place.
Seriously, think about it for a second. How did tech giants handle millions of data events per second without their entire systems just completely collapsing under the weight? Well, to understand the answer, we have to kind of rewire our brains. We have to stop thinking of data as this static collection of records just sitting in a database waiting around to be queried. Instead, we need to start picturing data as a flowing river. You know, a continuous, never-ending stream of events.
To unpack the secret behind this massive scalability, we've got a 6-step roadmap today. 1. The Event Stream Foundation. 2. Producers, consumers, and topics. 3. Decoupling with async messaging. 4. The power of the log. 5. Real-world e-commerce streams. And 6. The future of architecture. Let's get right into it.
Okay, let's dive into this with Section 1, the Event Stream Foundation. We're talking about a completely fundamental shift in how we handle the flow of data between processes.
Now, technically speaking, an event stream is defined as an unbounded, incrementally processed sequence of immutable facts over time. Let's break that down because it's a bit of a mouthful. Unbounded simply means it never really ends, right? The data is incrementally made available over time, kind of like a continuous live audio or video feed. And an event? Well, that's essentially a small, self-contained little package containing the details of something that happened at a very specific point in time. It might be a user clicking a button, a smart sensor taking a temperature reading, or maybe just a metric coming off a CPU. The absolutely crucial key word here is immutable. Going back to that flowing river analogy, the data is constantly moving, and you can't change the water that's already flowed past you. An event is a fact. Once it's generated, there's no going back. It cannot be undone or overwritten. We can only append new events to the stream. And this principle of immutability is so powerful because it makes our systems vastly more predictable, highly auditable, and frankly, a whole lot easier to debug.
Let's move right along to Section 2, producers, consumers, and topics. We need to build up our vocabulary for this new world and map out exactly who is interacting with this river of data. In this streaming ecosystem, we really have 3 main concepts to grasp. First up is the producer. This is simply the sender that's actually generating the event. Second is the consumer. That's the recipient actively processing the event. And finally, we have the topic. Because, let's face it, you don't just want one massive, chaotic river of data washing over everything. So, events are grouped together into named streams called topics. Just think of topics as specific radio channels that producers broadcast onto and consumers intentionally tune into.
And this brilliantly illustrates what happens when multiple consumers want to read from a topic. We typically use 2 main patterns. With load balancing, each message is delivered to just one consumer within a group, which is great for sharing the heavy lifting. But with the fan-out pattern, the exact same message is broadcast to all consumers, entirely independently. This is awesome because it allows completely different systems, say a search indexer and a real-time dashboard, to tune into the exact same stream of events without stepping on each other's toes.
Now that we know the players, let's look at the incredible architectural benefits of doing things this way. Section 3, decoupling with async messaging. So, traditionally, microservices communicate using direct synchronous network calls, things like REST or RPC. The problem here? Well, if Service A calls Service B, and Service B is running super slow or is completely down, Service A is just stuck there waiting. They are tightly coupled. Asynchronous messaging completely flips this script. A producer fires a message over to a broker and immediately forgets about it, moving straight on to its next task. The sender literally doesn't even need to know the IP address or port number of the recipient. It's a total game changer.
This decoupling is honestly revolutionary for system reliability. The message broker acts as a shock absorber, a buffer. If a consumer goes offline or just gets totally overwhelmed by a massive spike in traffic, it doesn't crash the producer. The producer just keeps happily pouring events into the river, and the consumer? It simply drinks from that river at its own pace whenever it's finally ready. This setup prevents small, localized faults from cascading into catastrophic, system-wide failures.
Moving right along to Section 4, The power of the log. Let's peek under the hood at the specific underlying technology making these modern event streams so incredibly robust.
Now, we just said a consumer can drink at its own pace, but that raises a pretty critical question, doesn't it? What happens if a consumer outright crashes, restarts an hour later, and has completely fallen behind the fast-moving stream? In older traditional message queues, once a message is delivered, it's deleted. Poof! So if the consumer missed it, it's gone forever. But modern architecture solved this problem beautifully using log-based message brokers.
Now, what's really interesting about this setup is that the solution lies in a partitioned log, like you'd find in Apache Kafka, for example. A log is simply an append-only sequence of records written directly to disk. To scale this up, the log is broken into partitions spread across multiple machines. Every single message inside a partition gets a monotonically increasing sequence number. We call that an offset. So the consumer simply tracks its own progress just by remembering its last offset. And because these log-based brokers write everything durably to disk and don't instantly delete messages the second they're delivered, we gain a literal superpower: replayability. If a consumer crashes, when it reboots, it simply looks up its last saved offset and resumes reading right exactly where it left off. But it gets better. You can intentionally jump back in time to offset 0 and completely reprocess historical data. If you accidentally deploy a bug, you just fix the code, rewind the offset, and replay the stream. It's basically time travel for your data.
Let's ground all these abstract concepts in reality for a minute. Section 5, Real-World E-Commerce Streams. Let's see how this actually looks when you're building a feature we all use every day, an online shopping cart.
Imagine the life cycle of an online purchase. In an old-school monolithic synchronous system, you have one massive transaction that desperately tries to validate the cart, charge the credit card, and reserve the inventory all at the exact same time. If any one piece fails, the whole thing rolls back. It's fragile. But in an asynchronous architecture, we break it down into discrete events. Step 1, a user clicks buy, appending an order-placed event to the log. And that's it. The user immediately gets a success screen. Then, completely asynchronously, the payment service consumes that event, charges the card, and emits a new payment-authorized event. The inventory service then consumes that event to reserve the item. It's a smooth, decoupled chain reaction.
And remember our principle of immutability here. If a user removes an item from their cart or cancels their order, we absolutely do not go back and delete the original order from the database. Deleting destroys valuable information. Instead, we append a brand new cancellation event to the stream. By keeping the complete true history of user intent, we can feed this stream into an analytics system later to study exactly why users abandon carts. That is something you simply cannot do if you just overwrite the data.
Well, this brings us to our final section, and really the core paradigm shift of this entire explainer. Section 6, the future of architecture.
So the crucial point is perfectly summarized by distributed systems pioneer Pat Helland, who said, "The truth is the log. The database is a cache of a subset of the log." Now, I want you to let that sink in because it flips everything we've been taught as developers totally upside down. The traditional relational database isn't the true system of record anymore. The ever-growing append-only stream of immutable events, that is your actual system of record. Your databases, your search indexes, your caches, they are all just materialized views derived from that one central log.
Treating your data as an asynchronous stream of immutable facts grants you some massive advantages. Your system becomes easily auditable because you literally have a perfect, unalterable history. It's highly scalable because producers and consumers are totally decoupled. You gain localized fault tolerance because slow consumers aren't going to drag down the whole app. And you get reproducible state because you can always rebuild your databases simply by replaying the event log from the beginning.
I want to leave you with this final provocative thought. If your database is really just a cache of the past, what new systems could you build by replaying your event log today? Imagine just spinning up a brand new machine learning model or a totally different search engine architecture and instantly hydrating it with years of rich historical user behavior just by plugging it in as a new consumer to your event stream. It completely changes the way you think about building software. Thanks for joining me on The Explainer, and keep building.